All right, we're going to look at gases now. And gases behave a little differently than most other things. We're going to start off with, first of all, just a little bit of an introduction to some common gases and their applications. I'll let you read through this list. You're probably familiar with some. Others may be kind of a new enlightenment to you. Our atmosphere, of course, is 78.1% nitrogen. It's inert. We breathe it in, we breathe it out. It does nothing for us, nothing against us. Oxygen we need, it's about 21%, just under 21% of our atmosphere. Then we have argon, which again is inert, and carbon dioxide, and neon, and helium. And then there's a whole bunch of other gases, pollutants mostly, which make up very, very small proportions of our atmosphere. The macroscopic properties that we are going to be, that are available to be looked at are listed here. The ones we're going to focus on are temperature and volume and pressure, and then of course mass as well. Now, pressure is a new property that we haven't really looked at before in any of the science courses, unless you've done a little bit of physics. Pressure is the force per unit area, and you'll notice that there's a whole bunch of units available for that. Now, I'll have another slide to explain a little bit more on that. Volume was the space that's occupied by the gas, and we're going to measure that in liters. Which is more of a capacity. We could also use cubic centimeters, cubic meters, that sort of thing, but we'll use liters for our purposes. And then we have temperature, which is of course the average amount of kinetic energy in the gas, and we normally measure that in degrees Celsius. I'll explain a little bit of a problem when we get to the second gas law, Charles' law, but we're going to start using another unit called the Kelvin. Mass, of course, we've been using all along, and so when we get to the ideal gas law, we'll start introducing that as well. There are several different types of motions. We're going to use our kinetic molecular theory, which is the working theory for how gases behave at normal temperatures and pressures. The types of motions that we will experience are vibrational, rotational, and translational, and these different types of kinetic energy or types of kinetic motion will reflect on how much kinetic energy the gas molecules have, and relates directly to the temperature. So the points of the kinetic molecular theory are as follows. The first is that the volume of an individual gas molecule is negligible compared to the volume of the container holding the gas. So in other words, gas molecules are tiny, they're really far apart from each other, and therefore the container that they're in is really mostly empty space. There are neither attractive nor repulsive forces between gas molecules. Gas molecules have a high translational energy. They move randomly in all directions and in straight lines. When gas molecules collide with each other or with the walls of the container, there's no loss of kinetic energy. Okay, so that means that we call them elastic collisions. And the average kinetic energy of gas molecules is, of course, directly related to the temperature of the gas. Now, this is where we talk about pressure. And what happened back in history is that in the mid to late 1600s, there were a whole bunch of scientists working on gases and trying to figure out, okay, what's going on here? And inevitably they had to deal with pressure. And so as a result, being, at that time they were not so communicative, they weren't able to relate to the other scientists who were working in the same field as easily. And so as a result, we have all these guys coming up with their own units. And for some reason, they've all kind of hung around. And in different applications, we tend to use certain units. And so we have millimeters of mercury torr, which is named after the Italian physicist Evangelista Torricelli, who was quite full of himself. It's in fact exactly the same unit as the millimeters of mercury. We have atmospheres, we have pounds per square inch, we have pascals, bars, kilopascals, and so we of course need to be able to convert from one unit to the other. So here are the unit conversions down here at the bottom. 1 atmosphere is 760 millimeters of mercury, which is 760 torr, which is 14.7 psi, which is 101.3 kilopascals, which is 1.013 bars, and you'll just have to make conversions whenever necessary. Whenever there are two pressure units in your equation, the units have to be the same. All right, so let's look at Boyles Law first of all. Boyle essentially came up with the idea that volume and pressure are inversely proportional with each other. As the one goes up, the other one goes down. And so relating that mathematically, we have V is proportional, that's this alpha, the Greek letter alpha. V is proportional to 1 over P. Okay, so that makes P times V essentially a constant. And so we get the relationship P1 V1 equals P2 V2. And that is Boyle's Law. So here's how it works in terms of an example. If we have a balloon, has a volume of 5 liters, filled with air at 101 kilopascals, and we take that balloon up to the mountains where the pressure is 682.7 millimeters of mercury. If the temperature is constant in both places, what's going to be the new volume? All right, so writing down first of all the information that we're given from the question. We have our initial pressure, we have our initial temperature, volume, and then our final pressure, you'll notice, is a different unit, so we have to convert it to the same one. You can pick either one. I chose to go with kilopascals, and so we convert the millimeters of mercury to kilopascals. So 101.3 is the same as 760 millimeters of mercury, so essentially this, we're just multiplying by 1. And so the units cancel, and we're left with kilopascals, so that's 91 kilopascals. And so P1 V1 equals P2 V2. Solving for V2, we get 5.5 liters. All right, so that's kind of a classic example of Boyle's Law. Here's the one other thing that we need to deal with is that it's quite often a little bit easier to give information in terms of standardized pressures and temperatures. And so we've come up with a standard temperature and pressure of 0 degrees Celsius and 1 atmosphere. We call that STP. And so sometimes in a question you will be given such and such happens at STP. And so right away you know it's 0 degrees, 1 atmosphere. It's a little bit easier to communicate that information. Now, the problem with STP, of course, is that 0 degrees Celsius is cold, and nobody likes to work at 0 degrees Celsius. And 1 atmosphere is what you usually have at sea level, and most labs are a goodly distance above sea level, and so the atmospheric pressure is usually a bit less than 1 atmosphere. And so what we've done is gone and made up a standard ambient temperature and pressure, which is a little more comfortable to work in, 25 degrees Celsius, and more realistic pressure of 100 kilopascals, a little bit less than 1 atmosphere. So these are ways of giving this information. So if you see at SATP or at STP, then right away you know what these specific temperatures and pressures are going to be. And yes, you have to memorize them. All right, so here are the homework questions. Try these, bring questions to class, so we'll talk about them there.